Has everybody got their 2 pages? We need to get started. Okay, this first PowerPoint is a short PowerPoint that gives you the basic ideas and concepts of the next part of inference, which is an introduction to something called hypothesis testing. So what we were doing last time was we were making estimates. In other words, we were making predictions. What do we think will happen? Okay, what do we think the mean is? What do we think the proportion is? This is about verifying something someone else thinks. So this is not making a prediction. This is testing someone else's prediction, is what this is all about. So first of all, we need a definition of what a hypothesis is. Does anybody have any idea that's taken maybe a science class knows what a hypothesis is? It's exactly what it is. It's an educated guess. It's not just some wild random guess. It's a guess based on some evidence. Okay? Now, the dictionary definition is that it's a tentative assumption made in order to draw out and test its logical or empirical consequences. It's an educated guess. Okay? This is a hypothesis. It will rain tomorrow. The hypothesis may be true or it may not be true. If the first hypothesis is not true, then the second hypothesis is true. The first hypothesis is going to be something we call the null hypothesis. And basically that null idea comes from the word not. And the word not is actually implied when we get into the next chapter and talk about differences between 2 population means or between 2 population proportions, because the null hypothesis will say there is not a difference between. And then of course the opposite to that is, well, yes, there is a difference. So in this case, what the null hypothesis is saying is there's no difference in the truth being that it will rain tomorrow. And then the alternate is saying, no, the truth is it won't rain tomorrow. Okay? The null and the alternate hypotheses cannot say in any way the same thing. They have to be 2 completely separate things. In other words, they need to be disjoint. That was the word that we learned in chapter 4. That 2 things that cannot happen at the same time are disjoint. These 2 things must be disjoint. Either it will rain tomorrow or it won't. Now that's what's going to happen in fact. So that's the null hypothesis and that's the alternate hypothesis. Be sure that you get in your mind the difference between the 2, because the null says this is, and the alternate says no it isn't. Okay? So HO, it will rain tomorrow, could be true, or it might be false, which leads to 4 different potential outcomes for a hypothesis test. If HO is true, it will rain tomorrow. If HO is not true, then the sun will be out. If you decide, based on whatever evidence you choose to look at, either looking out your window, listening to a weather report, hey Siri, what's the weather like today, whatever, if you decide based on the evidence that you look at that you think HO is not true, then you have rejected HO. You're saying HO is not true. I reject HO, that's not true. It's not correct. If that happens, 2 things could still be the fact. And again, if you look out the window, ask Siri, hey, what's the weather today? Watch a weather report, pick up a newspaper, read the weather forecast, you might accept HO. You would decide that HO is probably true. Based on your evidence, you think that it is going to rain today. Now, what could happen with these scenarios is that you could make a type 1 mistake. A type 1 mistake is if HO is in fact true, it is going to rain today, and you have rejected HO, which is why the raincoat and the umbrella are sitting at home and not with you, because you decided it wasn't going to rain. So you left those things at home. Making a type 1 mistake actually has a definable probability. And when that definable probability occurs, this is what happens to you if you make the type 1 mistake. You're standing at the bus stop or in the parking lot soaked because you said, no, it's not going to rain today, and you were wrong, which is why it's an error. The probability of making that kind of mistake is called alpha. We've talked about alpha before, and alpha has not changed its role. Alpha is the probability in the tails of a normal distribution. Okay? If, on the other hand, you decide that HO was not true, and in fact HO is not true, did you make a good decision? Yes, you recognize that HO was incorrect. In that case, you made a correct decision. Whoops. And the result is you go to the beach and get sunburnt, but at least you don't get rained on. Okay? Now, there's another possibility. You could accept HO, which means you carry your umbrella that day, and HO is in fact true. So that was a correct decision. You decided it was going to rain, and it does rain. So you carry your umbrella, and you don't get wet while it rains. You can walk in the rain and stay dry. But you could also make a mistake by accepting HO. Because you could accept HO because the weatherman said it's going to rain, the newspaper said it's going to rain, Siri says it's going to rain, and in fact, for whatever reason, if you live in East Tennessee, you know there is no guarantee that anybody is ever right about the weather, and that means that you might make a type 2 mistake. Notice that's different from type 1. Type 1 is when you reject the truth. Type 2 is when you fail to reject a lie or an incorrect conclusion. If you make a type 2 error, well, you get to carry your umbrella all day, but at least you didn't get wet. Okay? So there are consequences for making either of these kinds of errors.
That'd be erring on the side of caution, wouldn't it?
This is erring on the side of caution, and this one is not. This one also has a probability. Its probability is called beta. It's a little harder to calculate risk based on beta, so we usually focus on not making type 1 mistakes. But in this case, the type 1 mistake would be the more serious mistake of the two because you're going to get wet. Whereas here, okay, you carry, a few extra ounces in your umbrella. There's always either type 1 mistake or type 2 mistake always come with consequences. The question in your mind is always going to be, which one has the worst consequences, making a type 2 mistake or making a type 1 mistake? Because that's always going to be the thing you want to consider, and then you want to try to minimize making the type 1 mistake. And you can actually manipulate that, the possibility of that by changing the value of alpha. Because if you raise alpha, you lower beta, but if you lower alpha, you'll raise beta. They do not operate at a 100% level. Alpha plus beta does not equal 1, because both of them are the probability you made a mistake. Alpha plus beta plus the probability you were correct in both the other ways would equal 1. But alpha and beta simply, if one is high, the other one is lower, and if you lower one, the other one goes up. They operate that way. In the procedure that we're going to use in this chapter, the beta risk is not defined. It'll never be defined. We don't have a way in this course to be able to define beta and control for beta. We do that in the statistics methods for business class next semester if you are a University of Parallel Business major, but not in this class. So based on not knowing what the beta risk is going to be, what we want to do is never, ever, 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 ever say, I accept the null hypothesis. You don't want to accept a lie, because we can't calculate the risk of accepting a false statement as truth. So you never say, I accept HO. And that's very important. You never say that in any of your conclusions to any of our problems. You never say that. You never say, I accept the null hypothesis. And that's because the beta risk is unknown. You can't calculate for that. In statistics, you only want to say things that you are pretty sure have a low risk of being wrong, which means we're going to talk about the alpha risk. In the procedure we're going to learn, and I'm sorry you can't see that because the projector is aimed so terribly. Maybe I can, nah, I'll have to work from there. In the procedure we're going to learn, the alpha risk is defined because we're going to know what alpha is. It's going to be given in the problem. And it's going to be very small. 0.05, 0.04, 0.025, 0.01. If it's something where it's a life or death consequence, if you make that mistake, it would be probably 0.001, 1/10 of 1%. That's a common level of alpha in medical practice. So it's going to be defined and it's going to be very small. And then you can say, I reject HO, and have a very, very, very small probability of being wrong. Okay? So based on the data, which is your evidence, you can say one of two things. I reject the null hypothesis. The null hypothesis is not true. The evidence does not support the null hypothesis. Or I can say, I do not reject the null hypothesis. Does that mean that you accept the null hypothesis? Not quite. Think about a trial by jury. When the jury says, we find the defendant guilty, what do they base that response on? Based upon beyond a reasonable doubt. We find the defendant guilty based upon evidence that has convinced us beyond a reasonable doubt that this person did what they've been accused of. Now, what is the other verdict that a jury can bring back to you? Based on the preponderance of evidence, we find the defendant not guilty. Okay? Does that mean that the jury really thinks the person is innocent? No. It just means they didn't have enough evidence to find that the person was guilty. Now, it may very well be that the person was guilty. That is a possibility. And that person will go free because there was not enough evidence to prove to a reasonable person that that person actually did what they were accused of doing. Now, if that person actually did it and walks away, that is a mistake. But we want a small probability of that happening. So is saying I will not reject the null hypothesis the same as saying I accept the alternative? Is saying not guilty the same as saying they didn't do it? Not quite. It's not quite the same thing. So that's why we can say I don't reject the null hypothesis, which might very well mean I still think it's wrong. I just don't have any evidence to prove it. Okay? So rejecting the null hypothesis is the same as accepting the alternative with the reservation that you're not saying I accept it. I'm just saying I don't have enough evidence to reject it. Okay? Might sound like semantics, but when you think about the trial by jury, it makes sense. And H1 is what HO isn't, so it's saying basically, well, the evidence kind of supports that H1 was true, even if I might not believe H1 was true. So we're going to look at 4 examples related to hypothesis testing to get you into the idea of how this works. Now, Mrs. Borlaug is my friend. You do not know Mrs. Borlaug. But we have been friends for a very long time, which will give you a little evidence about Mrs. Borlaug and me. Really is annoying. So, if HO says Mrs. Borlaug is young, and she's my friend, and we have a lot in common, we are both teachers, we both teach statistics, she works at a community college, I work at a community college, we both like animals, we both have similar interests in a lot of different outside activities. HO says Mrs. Borlaug is young. What does H1 say? She's not young. That's the politically correct answer. Do not say Mrs. Borlaug is old. Mrs. Borlaug may not be young, but she's not necessarily old. Okay? So H1 says Mrs. Borlaug is not young. That's really all H1 ever says. It's whatever HO said. No, it's not. The word not goes in there. Okay, here's your evidence. Here's Mrs. Borlaug's last birthday cake. A lot of candles, right? It had so many candles on it they had to call fire department. Does the evidence support HO or H1? It supports H1. So if HO were true, the data that we're looking at would be very unusual, right? So for that reason, we don't think HO is true. So we would reject HO based upon the evidence. But the sentence that you write at the conclusion of these is always going to be written in terms of the alternate hypothesis, not the null. The conclusion always references the alternate hypothesis. So if we have rejected HO, what does that tell us about the evidence? Does it support H1 or does it not support H1? It supports H1 because it didn't support HO.
So you would say there's evidence to support H1?
Yes, there is evidence to say Mrs. Borlaug is not young because she got her house done with a birthday cake. Okay? There is evidence to say Mrs. Borlaug is not young. Anybody have any questions so far? Okay, let's look at another example. Mrs. Borlaug owns a boat. That's HO. What would H1 say? Mrs. Borlaug does not own a boat. Just insert the word not. Okay, here's your evidence to look at. Miss Borlaug does own a truck. Why would that be relevant? That's right, you gotta have a truck to pull the boat. Many people that own boats are gonna own trucks for that reason. If HO is true, would this data be ordinary or unusual? That she owns a truck if she owns a boat? If HO is true, Mrs. Borlaug owns a boat, is the fact that Mrs. Borlaug owns a truck supporting that she might own a boat? Okay, so it would be ordinary. Now, a lot of people have boats and have trucks. So it wouldn't be unusual if you have a boat to have a truck. That would be kind of ordinary. So we come to that conclusion. And based upon that conclusion, well, the evidence that she has a truck seems to support the idea that she has a boat. So you would not reject HO. Okay? But we would write our sentence in terms of H1. And since H1 says she doesn't own a boat, is there evidence to say she doesn't own a boat? No. There is not evidence to say that she doesn't own a boat. We have no proof that she doesn't own a boat. Now, in this particular case, because I know Mrs. Borlaug, I can tell you that if we came to this conclusion, we would have made a type 2 mistake. Okay? Because the fact is, she does not own a boat. She owns a horse. So do I. And we have to have a horse trailer to haul the horse to the vet and to the riding trails and every place else. So, yes, the evidence supported that she might own a boat, but it also makes sense that she owns a horse. So don't take that hypothesis testing as 100% proof of anything. It is simply a very, very educated guess based on evidence. There is still always a possibility, a very small possibility, that you'll make a mistake. Which is why when you write your conclusion, you never say, the evidence proves that. You never prove that the null hypothesis is wrong. You never prove that it's right. You just say the evidence supports it or it doesn't, and therefore the alternate is either supported or it's not. This one says Mrs. Borlaug is afraid of heights. And then the alternate, of course, is that Mrs. Borlaug is not afraid of heights. There's your evidence. What do you think? You think she's afraid of heights? Nope. Doesn't look like it. If HO is true, would the data be ordinary or would it be unusual?
Unusual.
It would be unusual if she jumped out of an airplane carrying her math homework with a parachute, deserted a perfectly good airplane for no good reason, if she was afraid of heights. Now me, they'd have to kick me out of that airplane. They would have to pry my fingers off the doors. But apparently she's not afraid of heights. So if HO is true, the evidence that we're looking at would be very unusual. People don't go jumping out of airplanes if they're afraid of heights. Agreed? So in that case, should we reject HO or not reject HO? We should reject HO because the evidence does not support HO. And since the evidence does not support HO, what does it support? It supports H1. So we say there is evidence to say that she's not afraid of heights. Jumping out of airplanes, excuse me? That she's not afraid of heights. There's evidence that says she's not afraid of heights. Because the only people that are going to jump out of airplanes with carrying anything are people that are not afraid of heights. At least people that willingly jump out of airplanes. So the next one says it's Mrs. Borlaug's birthday today. We've already seen that birthday cake. H1 would say it's not her birthday today. It's basically just HO with a not stuck in it. Mrs. Borlaug is going shopping today. A lot of people go shopping on the birthday because they got money for the birthday, right? So does the evidence support that it's her birthday today? Yeah. She's going shopping, spend that birthday money. HO could be true. That would be ordinary. And in that case, we reject or don't reject? Do not reject HO, because the evidence says, well, it might be her birthday today, she's gone shopping. So that means we say that there's not evidence to say it's not her birthday. We have no evidence that it's not her birthday. Doesn't mean it is her birthday. We just don't have evidence to say that it's not her birthday. Okay? So HO is the null hypothesis, H1 is the alternate, and based on the defined risk, you will never be able to prove the null hypothesis because of the reason I explained to you that, you're never going to know if you're right or wrong. You have to make a decision. So you don't have definitive proof. The only way that you can prove the alternative hypothesis or support the alternative hypothesis is if the data gives you enough evidence to reject the null hypothesis. So you can sort of prove the alternate, or you can support the alternate with evidence that works against the null. So to have any chance of proving something, it's probably going to need to be in the alternate hypothesis. Okay? And contracts always have fine print, and the fine print is that unfortunately with just a sample, it's impossible to prove something that is equal to a value. So the equal has to go in the null. Okay? It is true that the mean is, that means the mean equals. The proportion of the population is, that means P equals. So the equals always has to go in HO. So, just quick review before we go on. Never say except HO, because the alpha risk will be the beta risk will be undefined. Alpha can be quantified, beta cannot be. And in statistics, you only want to say things that have a high or low risk of being wrong. Low. If the data is ordinary or unusual when HO is true, then there's evidence to say I reject HO. When do you reject HO? Is the data ordinary or is it unusual? When it's unusual. Rejecting the null hypothesis is pretty much the same thing as doing what with H1? Accepting H1. And then if the null hypothesis is rejected, then the appropriate sentence in terms of the null hypothesis is that there is evidence to say H1 is true, or there's not evidence to say H1 is true. You rejected HO, which is true. You rejected HO. What's left? H1. And if the evidence didn't support H1, HO, what did it support? H1. Okay? When the null hypothesis is true and there is not evidence to reject HO, and you say, I do not reject HO, what kind of data were you looking at? If you do not reject HO, what does your evidence say about HO? So it will be ordinary. the null hypothesis HO is not rejected, then you would say, which one of these two things? You did not reject HO. There is evidence to say that H1 is true. You sure? You did not reject HO. There is not evidence to say H1 is true. Remember, you can only accept or reject one or the other. It's an either or. So, what we're going to learn to do, and then I'm going to leave this and go to the next PowerPoint, is we're going to learn to set up the hypotheses given a problem, HO and H1. We're going to put what we want to prove in H1, but you remember that equals has to go in HO. We are going to define the critical region. I'm going to show you that approach, but we're going to use an approach that talks about p-values, and then use the data to find the test statistic. And then based on the data, which will be a comparison of the p and the alpha values, we'll either reject HO or not reject HO, and write a sentence in terms of H1. So at this point, we're going to leave this one. And pick up with this one. Now, the background here, we did confidence intervals for population means based on sample data with a sample mean, and sometimes a population mean, and sometimes a sample standard deviation. Sometimes we had a population standard deviation, sometimes a sample, and that told us whether to use Z or T. And we did confidence intervals for proportions, which was based on knowing a sample size and either p hat or the number of people in the sample that favored whatever it was we were looking at. When we're doing hypothesis tests, it works the same way. The hypothesis test for proportions is we're either given x out of n or p hat in n and a claim about the value of p for the population proportion. And when we do that, like we used 1 prop z interval, we're going to use a 1 prop z test to come to a conclusion about the test of a claim. If our claim is about a mean with sigma known, the population standard deviation, and we have x bar and n and a claim about the value of mu, we're going to use something called z-test. And that's because we know sigma. Sigma goes with z. If we don't know sigma, but we know s, then we're going to use t-test as a replacement for z-test, but it's going to be the same circumstances. If we don't know sigma, use t-test. If you do know sigma, use t-test. So this is going to be our steps. We're going to write the hypotheses and label the claim. Then we're going to decide on the sampling distribution, whether it's a normal distribution, which would be a z-test, either for proportions or means, or a t-distribution for means. Find the necessary sample statistics, which are going to either have to be given to us in the problem, or they're going to have to give us the sample data so that we can calculate them. And the p-value. The calculator is going to calculate what's called the p-value for you. Please do not get the p-value mixed up with the proportion that we're testing. The p-value is the probability of something happening. The proportion is the proportion or the fractional part of the population that are successes. make a decision about the null hypothesis. We're either gonna compare P to alpha, and that's the way we're gonna do it. We're gonna choose this one. We're gonna compare P to alpha because the calculator does it for us. And then we're gonna interpret the decision and write that sentence that we talked about. So here's the thing to really remember. This is gonna be very important as we put the information in the calculator. The null hypothesis, HO, is going to contain some statement of equality. It'll either contain an equal sign, an equal to or less than sign, or an equal to or greater than sign. There has to be an equals in HO. Professionally, we only use the equal to symbol, and what we usually do is just write the equal to or less than or equal to or greater than if that's appropriate, and then just change that to equals. So when I do these, I'm probably going to just say equals every time we do null hypothesis. Because the null hypothesis might say at least. That means it's this much or more, so the equals to is there. The alternative hypothesis contains a statement of inequality, which means it's either not equal to, I don't know if it's more than or less than, but I know that HO is not true. It is not equal to. Or it says the mean is less than, or the proportion is more than. But it doesn't contain equality, so it doesn't say at least or at most. It says more than or less than. What we're going to do is we're going to pretend that we are the jury in a trial. We're going to get in our little box and say, okay, I'm going to assume that HO is true. I assume the defendant is innocent until the evidence proves me otherwise. Okay? So we're going to assume that HO is true. This is regardless of whether the claim is represented by HO or by H1. You always go in assuming that HO is true. And then we'll collect data from a sample, it has to be a random sample, taken from the population and calculate the sample statistics. If the sample statistic has a low probability of being drawn from a population in which the null hypothesis is true, then you have to say the evidence doesn't support HO and you would reject it. And that means you'll support the alternative hypothesis. But if the probability is not low enough, then we'll fail to reject HO. If our evidence isn't strong enough to persuade us that HO is absolutely not true, then we have to say, well, I still think it's not true, but I don't have evidence to come to the conclusion that it's not true. I fail to reject it. So there's three kinds of hypothesis tests. You always look at the alternative hypothesis to decide which one of the signs to use. If you have what's called a right-tailed test, it's always going to say that mu or p is greater than. Your inequality sign is going to point to the right. If you have a left-tailed test, it's always going to say that mu, or the proportion, is less than some number. Your inequality sign is going to point to the left. It's a two-tailed test if your inequality sign is just not equal to. It doesn't specify less than or more than. It's just not the same as. That's referred to as a two-tailed test. A two-tailed test is a lot more conservative than either of the above, because it's much, much harder to have evidence to support H1, because the alpha risk here has to be split between both tails, and that means that being able to be in the tails becomes very, very small, even smaller than normal.
Do you go back and really down the book?
Okay? So right tail, alpha's in the right. Left tail, alpha's in the left. Right tail, mu is greater than, p is greater than. Left tail, mu is less than, or p is less than. If you don't know less than or greater than, if the problem doesn't tell you, it just says, no, this is not true, then you use the third one and split alpha between the two tails. Now, you're not going to physically split it yourself, because what your calculator is going to do is it's going to calculate the total p-value, which is half in each tail, and give you a combined p-value to compare to the combined alpha value. This is just a matter of visualizing how this happens. Now, what is the p-value? The p-value is the probability of obtaining a sample statistic with a value that's as extreme or more extreme than the one you got from the sample. Extreme means as far from the mean as you got. Is it likely that you got a mean that was so small and so far away from the mean, or so big and so much above the mean by chance, if HO was true? It's in the left tail for a left tail test, it's in the right tail for a right tail test, it's split between the two tails for a two tail test. This is ultimately how you're going to make the decision. This is one of the most important things you need to keep in mind. If you set the test up correctly, as long as you enter your information correctly, you set the test up correctly based on your problem, your conclusion should be a piece of cake. Because this is the most important thing you need to know. If the p-value that your calculator gives you is less than alpha, you reject the null hypothesis. And then therefore you would support the alternative. If the p-value, and this says greater than, if it's not less than, that's all you need to think about. If it's not less than, then you fail to reject the null hypothesis, which means the null hypothesis is probably true and the alternate hypothesis has no evidence to support it. Now, I'm going to let you fill in your blanks with this. The decision can also be made by comparing the critical value to the standardized test statistic. If the standardized test statistic is inside the rejection region, you'll reject HO. If it's not, if it's outside the rejection region, then you don't. I'm going to show you one time how that works, but the calculator is going to tell you. And then when you interpret your decision, you always look back at the claim. If the claim was the null hypothesis, then you'll either reject the claim or you will determine there's not enough evidence to reject the claim. If the claim is the alternative hypothesis, then you will either support the claim or you will determine there's not enough evidence to support the claim. Okay? So now we need to look at an example. Here's your first example. It's been reported that the average credit card debt for college seniors is $3,262 with a standard deviation of $1,100. Student Senate at a large university feels that their seniors have a debt that's much less than that. So it conducts a study of 50 randomly selected seniors and finds that the average debt is $2,995, with alpha equals 0.05. That's the area in the tails. Is the Student Senate correct? Well, we're going to have to figure it out. And maybe you already did. First of all, our choice here is which test. Is the problem asking us about a mean or a proportion? Did they make a claim about a proportion or a mean? A mean, because it says the average credit card debt for college seniors. What do they claim the mean is? What do they think the value of 3262? They think that's mu, okay? Where did that $1,100 come from? Of what? The population or the sample? Population, okay? So, there's mu, there's sigma. Based upon no more than that, the claim is about a population mean, and we know sigma. It is a z-test. So we get the calculator, and we choose z-test. Now, did they give us the data? Data meaning the actual raw credit card debt. Or did they give us statistics? They gave us statistics from a sample. So we're going to keep statistics highlighted. What do they claim that the mean is? 3262. What do they claim? What does the standard deviation seem to be based on the population? 1100. Now we're getting to the evidence. They collected a sample of 50 randomly selected seniors and found that the average is $29.95. What is $29.95 in statistics? That's X bar. And the N value is 50. Now this is the part that's very important. The rest of it you can kind of figure out with no problem. The line that we're on now, the one that comes right before calculator draw, is asking you, what does H1 say? What does H1 say?
It's less than the, yeah.
Okay. The student senate says their seniors have a debt much less than this. So when we pick a sign for H1, we need to choose the one that says less than. So you put your cursor on the one that says less than, and you select less than. Now we've got two choices after that, and for reasons I think that you'll enjoy, we're not going to do calculate. We're going to do draw. But before we, now I'm going to warn you, some of you are going to hit draw, and your calculator is going to go, quit. When that happens, you raise your hand. I'll kind of help you figure out why. Okay? Take your cursor down to the next line, take it over to draw, and hit enter. And my calculator should have had a fit, but it didn't because there's a scatter plot on there. So let me go turn the scatter plot off. Now, if you didn't get that, raise your hand. It doesn't give me a choice, you got to quit. The second, y equals, right, there's the problem. You can also just take your y instead, when you see the black box. Press enter, turn it off, and just go right next to your shift. When it gives you that, it's your y equals, and there's a black box right there. Put your cursor on it, press enter, and then go back to your steps again. It's a z-test or t-test if it's for a mean. It's proportion if it's about a population proportion. If you know sigma, it's z. If you don't know sigma, it's t. If it asks you for anything you don't know in the problem, you're on the wrong one. That's the best way right there. Get your wife. Clear that out. That should be it. Try again. You should be able to just run back down the screen. There you go.
So would it be possible for you to actually like write that down?
We're actually gonna do that. In fact, what I'm gonna do right here is, I'm gonna write some information down from the problem. Actually, maybe it'll print and not give me grief.
Yeah, because that's like the only thing that confuses me is like, I don't know when to use a certain thing on the calculator.
Somebody's got a set of notes up there if they need them. Okay. What I want to do with you right now is I want to go through the problem and make sure you understand what I want to see. So you read your sentence and it says it's been reported. Reported, stated, claimed. That's always going to tell you what your claim is. And when it says average, that tells you that your claim is about a mean. So that's mu. And the claim is that mu is equal to 3262. If this is the claim, we need to proceed further to figure out what else is happening. Student Senate feels that their seniors have a debt much less than this. Now that's the claim that was made by somebody with a lot of information. So maybe that's not the claim we're investigating. It says they feel that their seniors, so they're going to test, okay? They want to test this idea, and their test says less than. The claim is based on who's doing the testing. The person doing the testing makes the claim. The entity doing the testing makes the claim. So that means the actual claim that we're testing is that. And that's because this student senate is the people doing the testing. So they get to set the ground rules. They get to set up the test. Okay? So this is their claim. Now, based on what I told you about HO and H1, which one of these is HO? That's right. Because HO always says equals. That means that H1, in this case, is the claim. Okay? Now the next question you have to consider Z or T? Which do you have, sigma or S? You have sigma. Then it's a Z-test. Okay? Once you've determined that, the only thing else you need to do is go back through here. You've already identified mu. You told me this was sigma, so make sure you make a note of what it is. And then you're going to need the sample mean and the sample size. Your sample mean is 2995. Your sample size is 50. And then you also need to identify, and this has to be given to you, you need to identify the value of alpha. If one isn't provided, pick one. Okay? Pick one. Anything less than 5% is good. You can always assume 0.05 if you want to, but pick one. Usually it's given, but if it were ever not given, pick alpha to be 0.05 or less. So now that we've got all this information, we need to perform the test. We've chosen the Z-test. We've actually already conducted it. So I would want you to show me what's on that screen.
Do you want us to show you the picture too?
Yes, but you don't have to be really detailed about the picture. So when you draw, and you don't actually have to write draw because you're going to show me the picture. This is what you see. And I'll give you little normal curves that you can fill in appropriately. Now, this normal curve is based around the whole idea that this was true. The p-value that they gave us is in the left tail, which it should be because it's less than. And the area that's in the left tail is 0.043. And our test statistic is 1.7163. So that's what the calculator has told you.
My calculator did not show. How did you get it to show like that?
Oh, you got one of the new ones. I haven't seen them before, so. Oh, I think they did all right.
Isn't it negative 1.7?
Yeah. $29.95. Let me see that first one. There you go. Okay, yes, thank you, Zach, that is negative, because it's to the left of the mean. Now, the method we're going to use, the method we are going to use says we're not really worried about this. If they ask you what it is, that's what it is. That's the test statistic. But this is p-value. The p-value is 0.043. Alpha is 0.05. Which is smaller? The p-value. P is less than alpha. When P is less than alpha, you reject HO. Okay, you reject HO. This is not true. H1 must be true then. The Senate, based on evidence, is correct. U is in fact less than 3262. Okay? Yes. Now that we don't need that top part anymore. Too much paper. Okay? So you make a determination.
What is the question?
It says the Senate, based on, I just put blah, 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 because based on the evidence from the sample, is correct. The mean is less than 3262. Their claim is correct. Okay? And that's because P is less than alpha. Looking for a marker. Okay, don't have one. I guess I'll have to teach you to cheer. Here's how you decide. Everybody get ready. If P is low, HO's got to go. Say it with me. P is low, HO's got to go. Okay? Now, if you want to put words in there with that, that's okay with me. Because my students in the past have said, when P's low, the ho's got to go. Okay? If that helped you remember it, it's fine with me. The thing to remember is if P is low, HO is wrong. P is low, reject HO. Okay? My main goal is that you know how to do the problem. So, we could have written HO is equal to or greater than, because the opposite of less than is equal to or greater than. But the point is, there was an equal there. The only thing you needed to worry about was there was an equal there. Okay? And that's why it says the null hypothesis may simply be mu is equal to.
Well, the statement would have had to say is at least, but it just said is.
Yeah, it just says is. But if you're going to go truly with the dichotomy, then yeah, you have to include that. But really, statisticians just use equal to. It makes things a lot cleaner. Step 2 was deciding on the sampling distribution, which gets back to what I think Zach asked me, how do you know? Well, we decided that it was either Z or t-test because it was about a mean, okay? If it's about a mean, it's either z-test or t-test, and I will have a flow chart for you that you'll actually follow it out to decide what to do, and then it'll actually give you the calculator procedure to do at the end. Once you know it's Z or T, you look at the problem and say, do I know the value of sigma? Sigma was given. We'll use a Z distribution, which is the normal distribution. Step 3 is to find the necessary sample statistics and p-value. Finding the sample test statistic is just calculating the Z-score. That's what the calculator did for you. It calculated this by doing that with the information you gave it. It did the arithmetic. This is a left tail test because the alternative hypothesis was less than. So the p-value is the area in the left tail, also indicated by the fact that that is negative. The p-value is the area in the tail less than negative 1.71, which comes out to be 0.0436, which is the other thing the calculator did for you, so that you didn't have to do any of that.
Did they have these, when you started teaching, did they have these? Or did
When I started teaching, they had TI-82s that did most of this.
What did they do before?
Or, well, actually, no, I take that back. They had TI-81s,
What
which
did they
were,
do before these? Abacus, what did they do?
well, not an abacus, but pretty close. I still have my slide rule. Before this, when I actually learned to do it as a student many, many years ago at Walter State, we did it all by hand with a 4-function calculator that adds, subtract, multiply, divided. And we had a table that we had to look up areas under the curve with. So we had to do a lot more work than you have to do. And then eventually, and when we got to the end of our course, like you're taking now, at the end of the course, I remember everybody being so thrilled because we were taken into a computer lab and sat down in a machine with a computer terminal, not even an actual computer, but just a dumb terminal, running off a mainframe that we were allowed to access a program that calculated all this for us. And believe me, we were impressed because we had, I mean, it took half an hour to work this problem, okay? So this is what your calculator shows you, and that's what's, you know, exactly what you've seen. That way you don't have to worry about if your notes weren't complete. It's all there. If you had done this and you had done calculate rather than draw, you get the same information. I did want to tell you that. You do get the same information, which is the information shown here. You get the unrounded z-value, and you get the unrounded p-value. But I think it helps you, actually, myself, to see the graph, because it makes it click for you. But ultimately, your decision is made. You compare the p-value to the alpha value, and you conclude that because p is less than alpha, you reject the null hypothesis. Now, if you were doing it with critical values, this is the way that it works. If alpha is 0.05, your critical z-score that goes along with 0.05 in the lower tail here is negative 1.64, which means that your test statistic, the negative 1.71, actually falls within what's called the critical or the rejection region. So if it falls within the tail, if it's further past the critical value into the tail, then you reject HO. Which is less than 5%, because here's that 0.043 right here, this area to the left. Okay? So if you wanted to find the test statistic, yes, the test statistic, you'd have to use sample information. But if you need to find your critical value, you just use inverse norm 0.05. Inverse norm of whatever the alpha is. Okay? But you'll come to the same conclusion regardless of which approach you take. And taking this approach means the calculator doesn't give you everything you need to know. And I'll prefer the other one because it gives you everything you need to know to come to a conclusion. The main thing is that you be able to interpret the answer. Now, formally, if I were writing a report, if I were the student senate, my decision would say at the 5% significance level, there is enough evidence to support the claim that the seniors at that university have less debt than $3,262. And basically, I like that even better because it says the Senate's correct, because that tells you really the answer to the question. Now, we have more examples on the worksheet. I will work through a couple of those with you as time permits. We've got about 10 minutes left, so we'll probably get through one. So let's try one of those, and then I'm going to leave you on your own with the worksheet, and then pick up next time and make sure that you understand how to do them. And I think those are on your notes. Let me look and see. Yeah, because we skipped over all these questions. I will come back and go over those with you. But I want you to try writing them for yourself, and then I'll tell you what they are. Okay, let's try this one. Actually, if there's a copy of this already, I may just use it. Now, you've got this in front of you, so it doesn't matter that I'm maybe making it too small, I hope. Simple random sample of 40 recorded speeds and miles per hour is obtained from cars traveling on a section of Highway 105 in Los Angeles. Sample has a mean of 68.4 miles per hour and a standard deviation of 5.7 miles per hour. Is the mean speed of all cars traveling on Highway 105 greater than what is posted, which is the speed limit of 65 miles an hour? Who gets to decide H1? Or who gets to decide the claim? Not H1, but the claim? No. Because is there a claim made here?
No,
They're just asking a question. So we're the ones answering the question. That means we need to write a claim. What does the question suggest that our claim needs to be?
the mean speed of all cars traveling on the
105 or 65? Okay. The claim that is suggested by the question is that mu is greater than 65. If they have a posted speed of 65 miles per hour, what's the mean supposed to be? Now that's our sample. When they posted that sign, what was the highway department saying was supposed to be true? The mean is supposed to be 65 miles an hour. You're not supposed to go more than 65 miles an hour. You're not supposed to go significantly less than 65 miles an hour either. Okay? But they're saying the speed limit here is 65 miles an hour. Okay? That's what the sign says. We're testing this because we're testing a claim that the mean is more than that. And 68.4 is most certainly more than 65. But that doesn't take into account that everybody that passed that sign wasn't going 68.4 miles an hour. Some of them were going 70 miles an hour. Some were probably going 60. But the average speed for 40 people was 68.4. So, given these two, which one is HO and which one is H1? Okay. Because equals always means that's HO. And then once you've assigned HO, you don't have much choice for H1. Okay? Now we're on to the evidence. Random sample of 40. What does that tell us? That's right. Is obtained from cars traveling on a section of 105 in LA. The sample has a mean of 68.4. That symbol would be what symbol for the sample mean? That's X bar. I think now you're beginning to see why I told you those symbols were so important by the time you get to the end of this semester. And a standard deviation of 5.7. What symbol should I use for that 5.7? Heard somebody say S, because it comes from the sample, not the population. Use a 5% significance level. What has that told us? That's right. Now we're ready to grind the evidence and see what kind of p-value gets spit out. Question 1. Of the three, which one is it and why? Okay. It is a t-test because sigma is not known. It is a choice between z and t because it's about mu. So we go to a t-test. So we'll go ahead and get the calculator. And our input is going to come from statistics. We don't have the data. Our claimed mean is 65. Our X bar is 68.4. Standard deviation is 5.7. and our sample size is 40. What does H1 say? It's the fact that it's greater than, and I wrote on my notes there that H1 tells you that. Always remember that line, you need to know what H1 is, which is why it's so important that you follow those first 3 steps. Write the claim, write the opposite of the claim basically, and then decide which is HO and which is H1, because HO is going to give you this answer and H1 is going to give you this one. So you have to have the setup correct.
So do you put the, on U, which one is it? All the way to the right?
All the way to the right where it says greater than mu sub 0. This mu sub 0 that it's flashing on is referring to that number up there that you've told it. Your claim is that the mean is actually greater than that 65 that you entered at the top. And then you can calculate or draw. Now this is a right tail test because H1 said greater than, it's going to the right. And here's the conclusion of that test. Remember, this is what's actually in the middle of that curve. Your t-score is 3.7725. Which tells you it's way up there. But the question is, what is that p-value? And be very careful how you interpret that p-value. 0.0003. That's a very low probability of being wrong if we reject HO. What?
4 means you move it 4 decimal places to the right. Is it 3? No, always do 3 times 10, and so the
Yeah, 3 times 10 to the negative 4. And you do move it 4 to the left, but remember, it used to be after the 3. So you need 1 less zeros. Okay? So your p-value is 0.0003. Alpha is 0.05. Which one's smaller? Yeah, your p-value is very small. P is less than alpha, so your conclusion is
evidence does not support HO.
so we'll reject HO. Right off the top, that's what that means, reject HO. But then if HO is not true, evidence supports H1. Now, realistically, what does that conclusion mean? There is evidence to support that the mean is less than 65, or greater than 65. What does that mean in practical terms to that state trooper? They were speeding, it's time to pull out the ticket book, okay? So remember, these problems all have practical interpretations. Okay? Now, I'm going to leave you with the rest of them. If you can't finish the problem, that's okay. But what I would like you to do before I see you on Wednesday is I would like you to go through and pick out the pieces of information you know. Even if you don't know everything, you can't complete the problem. Pick out the pieces of information that you know what they are in the problem. If you can tell what mu sub 0 is going to be or HO's mu value, pick that out and write it down. If you pick out the sample information, write down what that is. If you can figure out what alpha is, write down what that is. And then I'll help you do the tests and write your conclusions. There is also some practice homework for Chapter 8, but it's not going to be due until the end of the week.